Thanks again. So in this presentation, what I wanted to share with you is that why we think it is so important to design a radically efficient data center network and how we can achieve that by using optical technologies and new architectures. So if you look in the past, how data center networking power has been scaled is actually quite stable. But we already stopped getting that nice scaling. And if you look a little bit beyond, actually, the power consumption of the data center network is starting to build up. You may still argue that, oh, the percentage of the total power consumption from the networking side is relatively small. But actually, because the scaling of this trend is going to be accelerating extremely fast due to some emerging new workload that is being seen in today's data center. One good example would be machine learning. If you look at the model size, how it has been evolved of machine learning models in the past few years, you can see that they have been increased exponentially. And already today, they are already orders of magnitude bigger than that a single processor can hold, which means that in order to run these machine learning models, we really need to provide high bandwidth connectivities over potentially thousands, even hundreds of thousands of those machine learning accelerators or processors. So this is why, if you look at the bandwidth that is being equipped by these state-of-the-art machine learning accelerators, they are already more than 1 terabit per second. So what does it mean? Let's look back on this chart again. For example, if we want to build a AI supercomputer that can provide high bandwidth connectivities to connect, for example, in this case, hundreds of thousands of these NVIDIA GPUs, we immediately gonna hit a power wall. And on the other hand, you can actually think of power as cost. That means building such a supercomputer is gonna be extremely expensive. And this is what we think why we really need to find a step change of the power consumption or the power efficiency of the data center network today. So how we can achieve that? In order to answer this question, let's have a look where these power consumptions are actually coming from. If you look at a link today in today's data center connecting accelerators to accelerators, they actually consist of multiple layers of electrical switches connected by most likely optical fibers equipped with transceivers. And if you look at the power breakdown, they're actually around 50-50. The good news is that industry already started to chasing behind this transceiver powers by introducing, for example, co-packaged optics. By shrink the distance between the optics and the ASIC can potentially give us some reduction of the power consumption of the transceiver. This is a great first step forward, but it doesn't provide the step change that we're looking for. Definitely not orders of a magnitude of reduction of the power efficiency. Because if you look at this pie chart on the right here, now the power is actually dominated by the switching power. So you then may argue that why we can't take the advantage of the nice Moore's law scaling in the electronics. It is true in the past, but that scaling starts to slowing down to an end, mainly because that it is still possible today to put more and more transistors in a given area, but the power density also starts to cramping up, which means that in order to get better performance, we need to have to pay more power. And this is already worrying today. But as researchers, we want to look what's beyond that. And that's why we believe that by using optical technologies can potentially help us to continue the growth of this curve. The good news is that actually optical switching technology has been well studied in this community. I believe many of you are actually the pioneers in this field. And some of the technologies that's already actually compatible for some of the machine learning workload that is even available today, as for those that doesn't require fast reconfigurabilities. But we also need to look at what's beyond that, because the machine learning workload also evolves. For example, we start to see that the traffic flow will become data dependent, which means that it will pushing the switching time or the reconfiguration time of the optical switches much lower, potentially even in nanosecond scale. We still have a lot of technologies in the optical community today that can support nanosecond switching. For example, we chose wavelength switching. But the point that I want to make here is that we're not building nanosecond optical switches. What we try to build is a nanosecond end-to-end system, because no matter what optical technology that you chose, will definitely have implications in the other stacks or in the other layers of the whole networking stack. And the only way forward is that by applying a cross-layer innovation of the end-to-end system. And this is why we built this 4 nodes end-to-end system prototype that can achieve a less than 5 nanosecond reconfiguration time. If you are interested in this talk, please come to this, interested in our work, please come to this talk on Thursday that my colleague will give you more details. So by using co-packaged optics and potentially optical switching technologies, it can provide around approximately 5x reduction of the power efficiency. But the question here now is where we can find the other order of magnitude of reduction. And this is also probably why now we should looking at the transceivers again, because now you look at the pie chart on the right, the transceiver become dominant of the total power consumption again. So what would be the technology that we can adopt beyond CPO to provide further power reduction? If we look in the past, the link has been designed only focusing on achieving the bandwidth. So we evolved from 25G all the way up to 200G. But if now we set back all the constraints and only using power efficiency as our first citizen for designing the link, what would the channel look like? We did our first order of analysis. Here I plot on this graph here is the energy per bit as a function of data rate. Obviously, the absolute value may vary, depends on the hypothesis and assumptions. What I want to point out here is that it is super interesting to see this trend of the curve is actually bathtub, especially on the right-hand side. This actually agrees pretty well with some of the discoveries that has been shown in the other papers. And the main reason for that is the power sensitivity starts to increase significantly when the data rate increases, especially when the link loss is really high. So now if we start to design a link based on this discovery here, that means we probably want to optimize our channel data rate to around 10 to 20 gigabits per second. So how would that whole architecture look like? If you take today's 400G channel as an example, we can actually build it with 25 channels, each individually running at 16 gigabits per second. So we are moving from a limited parallelism to a massive parallelism architecture. This is really interesting because it doesn't only provide us with the reduction of power, what it can actually provide is other opportunities to design, for example, better topology that can help us to further reduce the power. And if you are familiar with the die-to-die or chip-to-chip connectivity industry, our architecture actually now is very similar to the die-to-die or chip-to-chip connectivity architectures where we're using parallel buses. So which means that we can introduce redundant channels with a very small overhead. This can help us to improve the fault tolerance, as we have heard many times in this workshop already. For example, if one link failed, we can easily switch on one of the redundant links. And we can also use those links to, for example, sending control signals or other informations that can help us to further simplify the transceiver designs, further reduce the power consumption. Obviously, this doesn't come for free. For example, one of the biggest challenges would be the packaging. And this is why we came here to seeking for help from this optical community, because I believe that in the past I've seen a tremendous development or improvement of packaging, how we can, for example, packaging photonic devices. And obviously, multi-core fibers with larger number of core counts also has been widely studied and potentially even deployed today. More extremely, actually, proposed by Professor David Miller from Stanford. Now, given that our channels is two-dimensional, we can potentially even think about free space optics for shorter distance applications. So with all these opportunities, I will conclude my talk. So we believe by using the sequence of these 3 steps, it can potentially provide us with this 10x reduction of power efficiency of the data center network. This is not just important for accommodate the requirement from these emerging workloads today. What is more important is this could potentially enable more fascinating and interesting applications that we will see in the future. Thanks.
Thank you so much. Now Wanwa will chair the rest of the session.